Hi everyone. So welcome to this supplementary video. So this question was raised today in class to sort of clarify some of the things like scaling analysis and perturbation expansion. So what I thought would be a nice thing to do would be to cover this problem that we have already done in class, DIN 3.2-1, and this is a 1D steady problem. So we already know the solution, but I wanted to kind of redo this problem from the lens of scaling analysis and perturbation expansion. So by redoing this example from a little bit more different perspective, I hope you can see how we can kind of relate different topics that we have been studying in part one. So I'll quickly redo the problem that we did in lecture 4, which is the 1D study problem. So it's a pseudo binary system with x is equal to 0 here, x is equal to L here. We have been given this is sort of a liquid phase here. You can imagine this is liquid, and here A is going to be with some sort of first order reaction. This surface is impermeable at x is equal to 0. So essentially, we have the case where we have an impermeable surface, and then we get some sort of a concentration has been given to us as C is equal to C and naught. Okay, so this is the problem setup. So it's a 1D study problem, pseudo binary, constant rho, because it's a liquid system. So liquid is stationary, so there is no velocity, and some gas is dissolving at x is equal to L, and the surface is impermeable at x is equal to 0. In the liquid phase, there is a first order volumetric reaction going on. Okay, so that's the system that we have. Um, Now, the next thing we need to do is kind of start with the governing equation that we had done in class. So governing equation is del CA by del T plus V dot del CA is equal to dA d square CA. Let's say del square CA now because still not simplified. Del square CA by del X square minus KVCA. So this is a problem. We'll say steady, this goes away. Velocity 0, stationary liquid, this goes away. So we get the equation d square CA by dx square is equal to KVCA. Okay, so this is a straightforward problem that we can kind of get as a dA d square CA. We get a straightforward equation. The second thing is boundary conditions. So boundary conditions. So at x is equal to 0, we have no flux. So this surface x is equal to 0. The boundary has no flux, it's impermeable. So we say dCA by dx at x is equal to 0 is equal to 0. And the second thing is CA at x is equal to L to CA naught. Okay. So we have the governing equation, we have the boundary conditions, and we can essentially solve them. This is an ODE, second order ODE, where the right hand side has a positive coefficient. So we get a sinh and cosh. For solving, before we solve, I'll just do a quickly, I'll say theta is CA by CA naught, and x tilde is x by L. And so the equation, and I'll define damp Kohler number to be KV L square by dA. So we'll get d square theta by dx square, damp Kohler number times theta, d theta by dx tilde is 0. 0 theta at x tilde equal to 1 is equal to 1. Okay, so this is the equations and boundary conditions, and this is the same thing we had done in class. And what you can say is theta is A1 cosh of A1 sinh of square root dA x tilde plus A2 cosh of square root dA x tilde, and then you can solve for A1 and A2 using the boundary conditions. And if you do that, you will find that A1 comes out to be 0. And what you really get is the fact that A2 is, and you'll get a value for A2, and you will get theta is cosh of root of dA x tilde by root of cosh of square root of dA. Okay. So this is the problem we get. So this is the concentration profile we get. So this is an example that we have done in class, and hopefully this was a good recap for you. But a question that you may wonder about is how can we apply scaling analysis to this problem, right? So that is one thing that you may want to think about is, can we apply scaling analysis to this problem? So what we had discussed in class next was, we have this example where we can expect that the concentration is roughly equal to 1, right? When dA is very small, concentration is roughly equal to 1, and then slowly within the pore, essentially we will start to see something like this, and start to see something like this. So this is the profiles for different Damkohler numbers, and this is the way Damkohler number will increase. So you will start to see faster and faster depletion of theta concentration, and this is again, remember that x tilde equal to 0, and this is x tilde equal to 1, and this is theta. Okay, so basically the more faster the reaction, the more depletion you will get in the concentration of species A. Now a question that one may want to think about here is, what is this scaling wise, what is this boundary layer thickness delta? Okay, so what is this boundary layer thickness delta? Can we estimate boundary layer thickness? And what I've seen sometimes, what ends up happening is that students say, well, why are we even thinking of boundary layer? Isn't the length L, which is the full scale, a natural scale for the length, for the concentration gradient? So that is our boundary layer thickness, is simply the length L. And that is what I want to basically stress about. Scaling analysis has to come from a place of sort of physical intuition, and then has to be combined with the governing equation. So let's assume that a student argues that the length scale for boundary thickness is simply L. Okay, so let's look at the equation. So this is an example for scaling analysis. Scaling analysis. And student argues, well, delta is really should be L. That's the argument. Okay, so the region of concentration thickness in dimensions is equal to L. So if that's the case, then I will say, well, the scaling analysis would mean delta Ca by delta square is equal to kV Ca, right? And this would mean that Ca, if you think about this, delta Ca is simply equal to Ca naught, because that's the only change you can expect from going from Ca naught to 0, right? And Ca would also scale as Ca naught. And so if you do this, so if you substitute Ca as Ca naught here, delta Ca as Ca naught here, we'll get, and delta as L, and delta as L, what you will essentially get is, you'll get a relation kV L square by dA is equal to 1. Okay, and if you think about this, is that what we have done is we have over specified our scaling analysis system. By saying that delta is the length scale of L, we are saying that the diffusion on that length scale of L is balanced by the reaction. So essentially, that's why we get essentially the Damkohler number is on the order of 1. So rather than finding something delta here, which you see in the plot here on top, as a function of Damkohler number, by assuming delta to be L, we have essentially kind of made the problem in a way that we have specified the Damkohler number instead of finding the value of delta in terms of like Damkohler number. So we have over specified the system. So really, scaling analysis is driven through a physical understanding. We know that the concentration boundary layer thickness should change your Damkohler number, and we expect it to decrease with an increasing Damkohler number, as we can see in the plot. So rather than saying it is L, we'll find the value of it. And so if you don't make an argument, so if you don't make the argument, if you don't assume any value of delta, then we'll say it's dA delta Ca by delta square is kV Ca, and same things will apply. Delta Ca is Ca naught, CA naught, and what you will get is, you can verify this, you will get sorry, you will get delta is L by square root of KV L square by dA, or you will get that L into Damkohler's number times minus half. Okay, so this is what we will get as a scaling analysis, and this has more physical interpretation to it. Is that delta basically essentially would depend on Damkohler number, and when Damkohler number is 1, we still get back the delta is equal to L, which is what we were getting from the first part. So in a scaling analysis, problem is really governed by the physics of the problem, and then you substitute the value. So, and as you can see, this is what we get from the scaling analysis. Now, the one thing that I wanted to do is that can we actually check this value to be correct? Like we have the scaling analysis, so what? Can we really check this value? And the answer is we really can. So we know that the theta is really, of square root of dA x tilde by cos of square root of dA. Okay, and remember that what is this? This means that CA is CA naught cos of square root of dA x by L by cos of square root of dA. And remember that whenever we want to calculate delta, and as we have discussed, what we do is we take the derivative. We say minus DAB dCA by dx at x is equal to 0. This is what we essentially want to then calculate, right? So this is what we get, sorry, x is equal to L. So what we are now doing is we can calculate this, or rather we don't even need the DAB. We want to calculate dCA by dx. The idea being that we want to calculate the derivative at this point, right? This location, we want to calculate the shape of this curve, and that will depend on Damkohler number. So we calculate that at x is equal to L. And if you do that, what you will get CA naught, and I believe you can verify this. This is not very difficult to do. You'll get sinh of square root of dA x by L, cos of square root of dA, and then you'll get square root of dA. You want to substitute x is equal to L, or this becomes CA naught root of square root of dA by L times tan hyperbolic of square root of dA. Okay, so this is what we get as dCA by dx. Okay, and we can expect that this would scale as CA naught by delta, because delta is the region of concentration boundary layer thickness. So if you do this, you'll get delta is L times square root of dA minus half, and tan h square root of dA, or basically rather, just to make sure, this is by tan hyperbolic square root of dA. Okay, so this is what we get as the exact result, or rather, so more exact result. This is the value we get. And you can see this is very similar to the value of what we got, but we have this tan hyperbolic number. And when Damkohler number is large, tan hyperbolic will approach 1. So when dA is much greater than 1, tan hyperbolic will start to approach this number. But when tan hyperbolic is small, then we'll start to, when Damkohler number is small, we'll start to see a different result. And that's because our scaling analysis is no longer accurate in that region, because maybe the gradients are becoming slightly, slightly different than what we expect them to be. So overall, essentially, as you can see, we match the scaling analysis based on the physics problem. And the only thing we need to do is really understand what we are after. In this problem, we were thinking about the concentration boundary layer thickness, and that's why we use the scale of delta. Okay, so hopefully this example gave you a little bit more insights into this problem and how we can think of scaling analysis. In the second video, what I will do is I'll pick up the problem from here and then go into perturbation expansion and discuss that. That is what will be the focus of the second video, will be perturbation expansion. So I look forward to seeing you in that video.